So today our discussion is going to be on your experiment number 5, which is how to employ mux and demux of 74153 and 74139 for arithmetic and conversion circuits. So these are the components required: the ICs, patch cords, and the trainer kits. Okay, so initially you will have to know as to what is the pin configuration. Okay, and ultimately once you know these connections, okay, then you can try and understand. Now if you see here, you have E1 is 0, E2 is 1, then mux 1 is selected, so which means this IC has an inbuilt mux. Okay, multiplexer. Can someone tell me what's a multiplexer?
It selects one particular pin.
Hmm, correct. So which means um, it is like, it has multiple inputs but single output, right? So we can even term it like parallel to serial converter. Okay, and your demux, okay, doing the opposite operation, right? So here we have the configuration when E1, okay, when E1 is equal to 0, and when E2, okay, you have your E2 here, 15th pin. When E2 is equal to 1, okay, then mux 1 is selected. Okay, similarly, when E1 and E2 both are 0, then mux 1 and 2 both are selected. Okay, when E1 is equal to 1 and E2 is equal to 0, then mux 2 exclusively is selected. When both are high, okay, then both the muxes are not selected. Okay, so if you can see here, this is like, normally when we take 1 and 1, okay, it means selection. And when we take 0 0, okay, no selection. But here it's the reverse. Okay, that is because this is active low. Okay, it's working on the concept of active low. So 0 0, I'm getting, uh, I'm not selecting any mux, and I'm selecting mux, and when it is high, I am uh, not selecting the mux. Okay. Now here you can see, okay, you have the select lines 0 0 0 1 1 0 1 1. Okay, so when 0 0 is selected, okay, when that's your combination for your select lines, then A naught, okay, A naught is considered. When 0 1, then B naught. When 1 0, then C naught. When 1 1, then D naught. So ultimately, whatever is selected, that comes across your output. And all this B, C, D is on don't care. Okay, so which means whatever may be the input, okay, whatever may be the criteria, these would not be selected. Okay, only A naught is considered, and that comes across your output. Okay, so only A naught is considered, and this E naught comes across your output. Okay, similarly, if I have this combination, which is 0 1, then only B naught is selected. Okay, and B naught comes across the output, right? So accordingly, we will be working out with things, right? So now you can see your mux 1 and mux 2 as to how they are actually configured here, okay, based on your input and select lines. So you have here uh, A naught, okay, A naught, A1, A2, A3, okay, then B naught, B1, B2, B3, then you have your S naught and you have your S1. So these two are select lines, okay, and all these AB are inputs, okay, and YA and YB are the outputs for mux A and mux B, okay, the first mux and second mux. So you can see pin number 6 is A naught. See, pin number 6 is A naught. So this is actually given in the order of the pin numbers, okay, but this is actually rearranged in the form of mux. Okay, so any doubts here, students?
No, sir.
Okay, fine. So once you know this diagram properly, okay, then it becomes easy for us to implement this. So how we will implement a half adder? Okay, using 74153. Okay, so this is the name of the IC 74153. So for half adder, as we know, we need 00011011. So first we build our truth table. Okay, sum is 0, carry 0. For 01, sum is 1, carry 0. Okay, when 10 also the same case, when it is 11, sum is 0, carry is 1. So first we try to build our truth table. Okay, once the truth table is built, okay, then we try to assign values. Okay, either we can take A, B as our select lines. Okay, and accordingly connect them. Okay, right. So YA is given to sum and YB is given to C out. So here if you see YB is the 9th pin and YA is the 7th pin, which means two types of outputs here. Okay, so from the first mux I will be taking the sum, from the second mux I will be taking the carry. Okay, right. So how do we code them? Okay, based on our select lines A and B. So AB is here, right? So this will act as S0 and S1. Okay, so if my AB is 0, 0, okay, then what's going to happen? Sum is going to be 0, carry is going to be 0. So which means both are going to be connected to logic 0. Okay, both are going to be connected to logic 0, and that is actually getting passed to my YA, which is sum. Okay, similarly when A is 0 and B is 1, okay, so when this happens, my sum will be connected to high and my C out will be connected to low. Okay, so these are my first set of inputs. Okay, and this is my next set of inputs. So here you can see that, okay, the first one is 0. Okay, this is the first value, okay, that is 0, and the C1, okay, the C1 is actually connected to 1, and then you can see that your C2 is also connected to 1, and your C3, okay, is connected to logic 0. Okay, similarly this is going to be for your sum, and this part is going to be for your carry. So in your carry you have 3 zeros and 1, so 3 zeros will be here, and the last one, okay, last one is connected here. Any doubts here, students, how the connections are done? Any
No,
doubts
sir.
here? Okay, so ultimately what we are trying to do here is this one is going to be by 0, it's going to be connected to 0, and this is going to be connected to 1, 1, 0. Okay, and here we are going to have 3 zeros, 0, 0, 0, and this is going to be connected to 1. Okay, so I have two values here, which is logic 0 and logic 1. So accordingly just connect them, and across YA you will get some, across YB you will get CO, right? So whatever is our truth table here, okay, this truth table, whatever values are there, we are just implementing it in our circuit. Okay, so only thing that you will have to know is your inputs. Okay, what pin numbers that you are going to do. Okay, see, you have here input A. Okay, input A 0, then A1, A2, A3, then B0, B1, B2, B3. So this will be acting as my A0, okay, A, and this will be acting like my B. Okay, and similarly, this AB is actually acting as my S1 and S0. Okay, and then you can connect them to ground and VCC accordingly based on your based on your truth table and based on your pin configuration. Right? So similarly, for your full adder also, okay, you will have the select lines, okay, and sum and carry. Okay, so you can see that sum and carry is here. Okay, similarly, YA is going to be sum, YB is going to be carry. Okay, now how they are connected, what we have done here is when C in is 0, first half it is 0. Okay, let me just annotate, become easy for you, right? So we will take this half here. Okay, so just divide the truth table like this. Yeah, just divide the truth table like this. Of course our outputs are simple, it's just going to be connected to the sum and carry. Okay, and here you have C in, okay, which is 0, and C in, which is 1. Okay, so here only my C in is 0 and C in is 1. And here if you can see, okay, it is having 0 0 0 1 1 0 1 1. Here also 0 0 0 1 1 0 1 1. So which means this can act as my S1 and S0. Okay, so here I can consider when C in is 0, what is my S1 S0? When C in is 1, what is my S1 and S0? Right, so accordingly those values can be mapped, or it can be connected either to high value or it can be connected to low value. Okay, so let's just see the diagram. Yeah, so C in is connected like this, and the output, okay, C in bar, which means this is our NOT gate 7404. So whenever C in is 1, okay, so that uh, complemented output is actually taken. And as we know here, okay, input A, uh, then A naught, A1, A2, A3, B naught, B1, B2, B3. So these only we are connecting in this fashion. Okay, so if you can see 0 1 1 0. Okay, so 0 1 1 0. Okay, so which means I'm giving C in is equal to 0 here. Okay, so if I give C in as 0 here, if I give C in as 0, what is this line going to be? What is be my output here? Here, what output I'm going to get, students?
1.
1, exactly, right? So this line is going to be 1, and this line is going to be 0. Right? So accordingly, you can just check that these are added, right? So you can see that you have 0 1 1 0, right? 0 1, then this is also 1, and this is 0. Okay, and for the other set also it's the same. Next, when my value changes, okay, when my value changes, when C in becomes 1, okay, then you can actually check. Okay, we will just check it out. Okay, when C is equal to 1, my sum should be 1 0 0 1. So 1 0 1. So this one C in is equal to 1. So 1 is here, right? And this is connected to, when I give 1 here, 0 will come. So which means 0 is here. Okay, so 0, I'm connecting to 0, right? And then my C2 is also connected to 0. Okay, then my C1 is connected to 1 because it's connected here, right? So this line is again connected to 1. So ultimately what we can do here is you can check for your sum and C out also, the same fashion, the same fashion. Any doubts here, students?
No, sir.
Okay, fine. Okay, so ultimately your C naught also is connected in the same fashion with this lower inputs B naught, B1, B2, B3. Okay, right. Now we will get into half subtractor. For half subtractor also, see, the concept that you should understand here is we are mapping values, right? Whatever values that we have here, we are just mapping those values onto our mux. Okay, it's not that we are trying to do something new. No, not at all. Whatever values are here, we are just mapping them to our mux and getting those values. That's it, right? So similarly here also your AB is going to be your select lines, and then this is going to be as good as your sum and carry. So difference and borrow. Okay. So we'll be using logic 0, logic 1. You want me to explain this, or is it okay? Students?
No, sir, it's okay.
Hmm. So the same thing, what we'll be doing here is pin number 7. Okay, we'll be taking, see here, pin number 7, you took your sum, and pin number 9, you took your CO. Similarly, here also, pin number 7 will be taking your difference, pin number 9 will be taking your borrow. Okay, so logic 0, logic 1, and then this will be the first section, okay, of difference, and this will be the section for borrow. This is going to be a select line 0, 0, 0, 1, 1, 0, 1, 1. Okay, and the same thing applies for your difference also. Here instead of C in, okay, I'm giving borrowing. Okay, similarly, you can divide this truth table, okay, in this fashion where B in is equal to 0. Okay, in this fashion you can divide the truth table. Okay, when B in is equal to 0 and when B in is equal to 1, I will get 0, 0, 0, 1, 1, 0, 1, 1. Again 0, 0, 0, 1, 1, 0, 1, 1. Okay, so my select lines are going to be here. Okay, and then my outputs are going to be, these are my outputs, right? So the same values are going to just map to our IC, and once the values are mapped, okay, you can get the outputs across your 7 and 9. Now, with regards to demux, okay, the opposite thing happens, right? So demux can also be called as serial to parallel. It can be called as serial to parallel converter, okay, because we are just giving one value, and multiple outputs come out, right? So one input, multiple outputs. So here we'll be using 74139. So here we used 74153. So for multiplexer, 74153, and for demultiplexer it is 74139. The values are also given here accordingly. Okay, and this is going to be uh, your pin diagram, okay, exclusively as to where your uh, S10, S20, S21, okay, then your outputs Y10, Y11, okay, all these are connected. So which means you will have select lines, you will have data inputs, and then you will have data outputs. So in data outputs, you have 0, 1, 2, 3. Okay, so select lines again will be 0, 0, 0. Okay, it can be I can take it as 3-bit combination, okay, from 3 zeros to 3 ones, okay, and here also I can make two divisions when S1 is 0 and when S1 is equal to 1, and I can get 0, 0, 0, 1, 1, 0, 1, 1. Similarly, here also I can get that, and accordingly these outputs can be taken into consideration. Now, when I say, okay, so when I say that a particular value, okay, 1 is selected, okay, let us say 0, okay, 0 means nothing, okay, and when I say 1, and then when I say 1, 0, okay, and 0, 1, 1, this is going to be the value, okay, then 1, 0, 0, okay, we will have these values. So accordingly, what we are trying to do here is we are trying to spread out the values based on our data outputs. So here, in order to get the function, okay, I think you must be remembering we had a question in the internal also to perform decoder, right? Using decoder, use decoders to implement adder with an OR gate, right? So the same concept can be actually seen here, okay? So you can see that 3-bit combination is taken. Okay, 0, 1, 2, 3, 4, 5, 6, 7, and uh, I am having this at 1, 2, 4, 6, uh, 5, 6, and 7. So wherever you have high values, okay, those min terms are taken and it is given here. Okay, it is given to my NAND gate. Okay, and similarly wherever these values are given high, okay, um, accordingly I will be taking those values and connecting to those particular pins. Okay, as I told you, these are your active low. Okay, so what is happening, I'm using a NAND gate here. Okay, because it has to do a inversion, and then whatever is the outputs will going to be the opposite. Okay, so do you all remember uh, the adder that we implemented using decoder? Yes.
Yes, sir.
Yeah, so the
Yes, sir.
same way like how we had connected the pin numbers, right, based on the min terms. So I can take this as 0, 1, 2, 3, 4, 5, 6, 7. So whichever at whichever min term it is giving us high. Okay, so at that min term exactly, we will be connecting the pins here. Okay, right. Uh, so the same thing applies for your subtractor as well. So developing the truth table is important. Okay, once you develop the truth table, then going with the select lines and or mapping those values becomes very simple for us. Okay, borrow and difference. So the same fashion. So I hope you all have understood the concept of multiplexer and demultiplexer, right? And I'll be sharing you a video. Okay, so just have a look at it, wherein I've explained it in detail. Okay, along with the practical point of view. Okay, so any doubts up till here, students?
Sir,
No,
are
sir.
there any separate ICs
Even
for full adder and half adder?
Separate? Sorry, come again.
Separate IC for
Uh,
full adder and half adder.
you can
Are
actually
there any separate?
no. What we do is, uh, in order to implement that, we use multiplexer because this one multiple functions you can do, no. So exclusively for adder and subtractor, we don't do that. Okay, we take the help of decoders, we take the help of mux because these can do multiple functions. So when I have a system which can perform multiple things, then why do I have to separately fabricate them, right? I don't have to manufacture them separately.
Okay, sir.
So I will use this one only, which can perform anything. So it's like I'm coding. Okay, I am coding. I am first developing my truth table, and then these values I'm just mapping to my uh, IC values, IC pins. Okay.
Okay, sir. Yes.
And, okay. So we'll meet again in the next lab. Okay. If any doubts or if any concerns, you can always get back, and we could have another meeting. No problem. Okay.